Let's begin discussing conditional execution using 32-bit values. Here k is a unsigned 32-bit variable. Here we're going to check to see if k is not equal to 0. If it's not equal to 0, we're going to execute this if body. To do this, we first need to test the value of k. We can do that by subtracting 0 from it. So here's going to be one approach to do that. We're going to clear W0. We'll do compare least significant word against 0. This is going to subtract W0 from k and set the 0 flag. We'll then do a compare of borrow on the most significant word of k. Recall that the Z flag is sticky with regard to compare of borrow, so this operation will reflect if the 32-bit word of k is 0 or non-zero after we do it. At this point, we need to determine what branch we need. We're going to skip around this if body if k is equal to 0. So that would mean the Z flag would be true in that case. So we're going to do a branch on 0 to the end if k is 0. If this branch is not taken, then we'll execute the if body. That will be for the case of k not equal to 0. Here's another slightly more efficient way of doing a 0 or non-zero test on a 32-bit variable. What we're going to do in this case is we're going to bitwise OR the least significant word with the most significant word. The only way that this value will be 0 is if all the bits in both the least significant word and the most significant word are 0. So at the end we can test the Z flag and have this structure in exactly the same way as before. This saves one instruction. As a note, other ways that we've done this test is that for 16-bit variables we used this approach right here, in which we simply moved the variable on top of itself. This would set the Z flag. You cannot use the same approach with 32-bit variables. If you do this, this Z flag right here is only based on the value of the most significant word. Another thing that we've done is we've done compare against 0. Unfortunately, there's not a compare against 0 of borrow, so this approach does not work. So you can either use either this test here or this test here for comparing against 0. Let's take a look at another example. This is going to say if k is not equal to 0, logical OR if j is equal to 0, execute the if body. Recall that for logical OR test, if either one of these tests is true, we're going to execute the if body. We're going to write this code in exactly the same way as we did for 16-bit code, except we're going to use the 32-bit testing method on these two variables. So here we're going to use the inclusive OR approach for testing k against 0. Recall from a logical OR that if this test is true, then we want to execute the if body. So if k is non-zero, we're going to jump to the if body. For this test right here, since it's the last test in this logical OR chain, we're going to want the false test. We're going to want to test to see if j is not equal to 0. That would mean the test was false, and then we would skip the if body. So here we're using the inclusive OR approach for testing j just like we did here. And on not 0, which is the false conditional test, we're going to skip around the end if. If we do not take this branch, it means that j was indeed equal to 0, and so we would need to execute the if body. Note that this inclusive OR operation right here has nothing to do with this logical OR operation right here. We were using this inclusive OR approach for testing for 0 or non-zero. If the conditional test had been a logical and we would still use this inclusive OR approach for testing these operands for 0 or non-zero. Let's look at 32-bit equality where we're checking for k equal to j. If that's true, we'll execute the if body. We're going to write this in the same way as we did our 16-bit code, in that we're going to do k minus j. The only difference is that we're going to use a 32-bit comparison for this. So to start off, we're going to move j, the least significant word of j, into W0. We'll compare that against the least significant word of k. Then we'll move the most significant word of j into W0. We'll use a compare with borrow of the most significant word of k against the most significant word of j. At this point, the Z flag has been affected. For a branch, we're going to want to skip this if body if k is not equal to j. So we're going to want to do a branch on not 0 to this end if. If this branch is taken, then it means that k was indeed equal to j, and we'll execute the if body. Let's look at a 32-bit greater than. We're going to say if k is greater than j, let's execute the if body. Again, we're going to do this in the same way as for our 16-bit code, except when we do this k minus j comparison, we're going to use a 32-bit comparison. So here's the 32-bit comparison, same thing as on the previous slide, where we're going to compare k against j. At this point, this branch would be the same branch we would have used in the 16-bit code. Here we're going to skip this if body if k is less than or equal to j. So branch always on less than or equal to the end if. If this branch is not taken, then it means that k is greater than j, and we'll execute the if body. So the good news is that all the if and loop structures from chapter 4 can be used. You simply replace the 16-bit comparisons with 32-bit comparisons. Let's take a quick look at 64-bit operations. Here we're going to do a 64-bit addition. We declared k and j as uint64, and we're going to add k plus j, stick the result in k. So first of all, we're going to need to declare a space for k and j. We'll need 8 bytes for each. This is twice as many as needed for 32-bit variables. We're then going to add the least significant word of j to k and store the result in k. At that point, we need to do the additions on the next 3 16-bit words in this 64-bit value, and we'll simply use an add with carry each time. Notice that this is straightforward to extend the 32-bit add operation to 64-bit operations or 128 bits or however wide you would want to use. In our 16-bit microcontroller code, we will rarely, if ever, use 64-bit operands, so we will not have any additional coverage on 64-bit operations. Up until this point, all of our examples have used unsigned data types. We've used uint8, uint16, and uint32 for 8, 16, and 32-bit wide data. We will now begin discussing signed integers, and these are the data types that we'll use for that. We'll use an int8, an int16, and an int32, which will represent a signed 8-bit, signed 16-bit, and signed 32-bit. The following slides are going to discuss how signed integers are represented in binary. As mentioned in the previous slide, up to this point we've been ignoring signed integers. We've also ignored fractional numbers and floating point numbers. We'll discuss these briefly at the very end of the semester. At this point, let's concentrate on signed integer representation. So the problem is with signed integers, here's minus 45 plus 27 minus 99, is that we now have a sign. And the question is, how do we encode this sign? That's an extra piece of information that has to be encoded in addition to the magnitude. So let's take a look at 3 different approaches to this problem. So one approach to representing signed integers is to use a signed magnitude representation. In signed magnitude, the most significant bit is reserved for the sign, and it's 1 if it's negative, 0 if it's positive. The remaining bits are reserved for the magnitude. Let's take a look at some 8-bit examples. So here's a positive 5. The sign bit will be a 0 because we have a positive number. The magnitude will simply be a 5. As an 8-bit number, it's simply 0, 5. For a negative 5, the sign bit's going to be a 1 because the sign's a negative. The magnitude will be the same as its positive counterpoint. So as 8 bits, a minus 5 is going to be an 85. We can also represent a positive 0. Here's the signs of 0, here's a magnitude of 0. Here's a negative 0, sign bits of 1, magnitude of 0, that would be a hex 80. On a number line basis, we can represent for an 8-bit range the numbers from positive 0 to positive 127 and a negative 0 down to minus 127. So a couple of problems with this representation. One is that there are 2 zeros, plus and minus 0. That's problematic. The bigger problem, though, is that if we use a normal binary adder and we do plus k plus a minus k, that does not equal 0, either one of the 2 zeros. So here we're going to take a minus 5 plus 5. So minus 5 is a hex 85. Add 5 to that, and we get an 8a. That's actually equal to a minus 10. What this implies is that we would have to have a separate adder for any instructions that worked on signed numbers so that that adder could actually produce the correct result. That means that all of our instructions would have to be different for any arithmetic instructions would have to be different for signed magnitude than they would be for regular unsigned numbers. So another way to represent signed numbers, signed integers, is called ones complement representation. To get the negative of a number, all we do is take the bitwise complement of its positive value. So here's a positive 5. We'll just write that in binary and hex. To get the negative version of this, we'll just bitwise complement all of these bits. So a minus 5 is going to be this, which is going to be FA. We still have the problems of a plus and minus 0. Here's a positive 0. Here's a negative 0. On a number line, we can represent from positive 0 to positive 127 and minus 0 to minus 127. So we still have the problems of a plus and minus 0. Addition is somewhat better. If we add two positive numbers, we get the correct result. We still get the incorrect result if we add two negative numbers, or if we add a negative and a positive. In that case, the result's going to be off by one least significant bit. So we would still need some different hardware and different instructions for operating on signed numbers if we use ones complement representation. 2's complement is a standard method for representing signed integers in today's computing systems. To get the binary encoding for a negative number, you take the positive representation, take the ones complement, and add 1 to it. You can also take the unsigned representation and subtract it from 0. This will be our preferred method of getting the negative the binary representation of a negative number in 2's complement. Some 8-bit encoding examples follow. Any positive number is simply going to be its magnitude representation. So here we simply get to convert positive 5 to hex 05. To get the negative 5 representation, we'll take the unsigned representation 05, subtract that from 0, and the resulting value will be the 2's complement representation, in this case an FB. There is only one 0. It's represented as 0. If you take 0 and subtract 0 from it, you will get the same value. For negative 128, we'll take the unsigned representation, which is 80, subtract that from 0, and we'll get a hex 80 as the 2's complement representation of a negative 128. On a number line for 8 bits, we see that there's only one 0. The negative range is going to extend to a negative 128. For n bits, the smallest negative number that can be represented is a negative 2 to the n minus 1. In this case, this is going to be 2 to the 7th, a negative 2 to the 7th. For the positive representation, we can only go to a plus 127, so the maximum positive number we can represent is going to be a positive 2 to the n minus 1 minus 1. So this number right here is going to be 2 to the 7th minus 1, which is going to be a positive 127. 2's complement fixes all the problems of the previous representations. We only have one 0, and we can use a standard binary adder for adding or subtracting 2's complement representation. For example, a plus 5 and a minus 5, if we add these together, will give us a 0. Let's cover the steps for converting a signed decimal number to its 2's complement representation. So we'll convert a positive 34 and a minus 20 to its 8-bit versions. The first thing is we're going to take the magnitudes 34 and 20 and simply convert that to hex. So 34 is hex 22, 20 is hex 14. In step 2, if it's a positive number, you're finished. This will be the 2's complement representation of a positive 34. If it's a negative number, all you need to do is take that magnitude and subtract it from 0. So we had 20 was a hex 14. To get a negative 20, we simply say 0 minus hex 14. We do the subtraction and we will get EC. That will be the 2's complement representation of a minus 20. Here's one more example. Let's say we want to convert a minus 60 to a 2's complement representation. First, we'll just take 60 and find out its magnitude, which is going to be 3C. Then, because this is a negative, we're going to subtract that from 0. So we'll say 0 minus 3C. Let's do the subtraction. C, we have to borrow here. That's going to leave that at F. That's going to borrow a 16 in there. C from 16, 12 from 16 is going to be 4. 3 from 15 is going to be 12, or C, and so the final answer will be a C4 as the 2's complement representation of a minus 60. Let's go the other direction. Let's convert a hex number to its signed decimal representation. Let's assume that these hex numbers here represent signed decimal numbers and that we're using 2's complement encoding. The first step will be to determine the sign. All we need to know to determine the sign is if the most significant bit is a 1 or a 0. If it's a 0, then we know that the sign is positive. If the most significant bit is a 1, then we know it's a negative. And looking at the hex digit, if this hex digit here is 8 or greater, then we know that the sign is negative. After determining the sign, we then need to determine the magnitude. If the sign was positive, then all we need to do is take this hex number and convert it to decimal. So in this case, a 64 will be 6 times 16 plus 4 is equal to 100. So this represents a plus 100. If the sign is negative, then we need to compute the magnitude of the number. And that's easy. All we're going to do is take that number and subtract it from 0. Note that a 0 minus a negative n is going to be a positive n, which will give us the magnitude. So we started with an f0, and we said we know that that's going to be a negative number. So we're going to subtract that from 0 to get the magnitude. So 0 from 0 is 0. We need to borrow into this digit here, so 15 from 16 is a 1. Now convert this to decimal and we get 16, so the magnitude of this number is 16. So a hex F0 is going to be a minus 16 in decimal. Let's review the rules for converting a 2's complement hex value to its signed decimal representation. First, if the number is positive, all we have to do is convert it to decimal. In looking at this number here, we see that the most significant hex digit is less than 8. That means that this number is positive, so all we need to do is convert this to its decimal value, and we get a positive 77. If a number is negative, then we need to subtract it from 0, convert that value to decimal, in order to find the magnitude. So here we have a value B3, and looking at this hex digit, it's a B that's greater than or equal to 8, so we know that the most significant bit of this number is a 1, which means that our number is going to be negative. So we know our sign. At this point, to get the magnitude, we're going to take B3 and we're going to subtract it from 0. We'll get a hex 4D. Converting a 4D to decimal gives us a 77. At this point, we know the number. We know that a hex B3, which is a 2's complement representation of a signed decimal, is the value negative 77. 2's complement overflow occurs when I do an addition or subtraction and I get a result that cannot fit in the number range. Let's do an example. Let's do a positive 127 plus a positive 1. I should get a positive 128. Let's do this in hex and binary addition. So we're going to do 7f plus 0, 1. We'll get an 8, 0. And looking at this number, this number as a signed decimal number is actually a negative 128. We know it's negative because its most significant bit is a 1. I've added 2 positive numbers and got a negative result. That is overflow. We got overflow because you cannot represent a positive 128 in 8 bits. The largest positive number that you can represent using 8 bits is a positive 127. How do I detect 2's complement overflow if I'm doing addition? That's easy. If I add 2 positive numbers and I get a negative numbers, that is obviously incorrect. I have gotten overflow. If I add 2 negative numbers and I get a positive number, again, that is incorrect and I have gotten overflow. I cannot get overflow if I add 2 numbers of different signs. So adding a positive and a negative numbers cannot produce 2's complement overflow. Recall that the carry out of the most significant bit was actually an unsigned overflow indication. It does not mean that 2's complement overflow occurred. I need a new flag to indicate that 2's complement overflow occurred. You can build Boolean hardware that operates on this principle to detect overflow. Another way you can do it is to take the carry out of the most significant bit and exclusive OR with the carry into the most significant bit minus 1. For subtraction, I get overflow if I subtract a positive number from a negative number and get a positive number. This is simply the same thing as adding two negative numbers and getting a positive number. If I subtract a negative number from a positive number and get a negative number, again I get 2's complement overflow. This is basically the same as adding two positive numbers and getting a negative number. I cannot get 2's complement overflow when subtracting numbers of the same sides. Now that we know about signed numbers, let's take a look at two new flags, the 2's complement overflow flag, which we'll just refer as the overflow flag, and a negative flag. The negative flag will simply be the value of the most significant bit after an operation. So let's do some additions here and interpret these hex values as either unsigned numbers or signed numbers. From this point on, if I ever have a signed integer, it will always be in 2's complement form. So here I'm adding a hex 1 to a hex FF. I simply use my binary addition and I get a 0. So in this case, plus a carry out. So in this case, I added 1 plus 255 and I got a 0. This is obviously the wrong answer. If these are unsigned numbers, I should have gotten a 256. The carry flag's a 1. That means I had unsigned overflow. As signed numbers, that's going to be a positive 1. This is a negative 1, and I got the correct result. And in fact, I added a positive plus a negative. I cannot get overflow in that case. So the V flag is a 0, and this is a positive number. The N flag is a 0. So here's an example of I've added two numbers under one interpretation. Under the unsigned interpretation, I got overflow. While if I interpret them as signed numbers, I did not get overflow. Now let's take an FF plus an 80 and do the addition. We'll get 7F as an 8-bit result. There will be a carry out of the most significant bit here. I added a negative number plus a negative number, and I got a positive result. So the carry flag, the overflow flag is going to be set to a 1. This most significant bit is 0, so the negative flag is 0. Interpreting these as unsigned numbers, that's going to be 255 plus 128. I get 127. As 8 bits, that's the incorrect result because I had an unsigned overflow as evidenced by the carry flag. In interpreting these as signed numbers, an FF is a negative 1, and 80 is a negative 128. When I added those two things together, I got a positive 127. Again, that's obviously the incorrect result, so I got signed overflow. Here I'm adding 7F plus 01. I get an 80. I did not get a carry out. The carry flag is a 0. I added a positive number plus a positive number. I got a negative number. That means that I do have signed overflow. This hex digit here is 8 and greater, so that means that the negative flag is a 1. In interpreting these as signed numbers, I have 127 plus 1 is 128. That's correct, as evidenced by the fact that the carry flag is a 0. If I interpret these as signed numbers, a 7F is a positive 127, a 1 is a positive 1, and when I added those two things together, I got a negative 128. That is obviously the incorrect, so I have signed overflow. Finally, let's add 80 plus 20. I will get a 0. I have no carry out, so I have carry equal to a 0. I added a negative number plus a positive number. When I add a negative plus a positive, I cannot get overflow, so V is equal to a 0. The most significant bit of this 8-bit result is a 1, so the negative flag is a 1. As unsigned numbers, I have 128 plus 32. I got 160, which is the correct result. As signed numbers, an 80 is a negative 128, a 20 is a positive 32. I add those two together, I get a negative 96. If I do the conversion, A0, that is indeed a negative 96, so I got the correct answer, as evidenced by the overflow flag being 0. Let's review the rules for extending the range of an unsigned number. If we want to add more bits to an unsigned number, all we do is simply add zeros to the left. For example, a decimal 128 is an unsigned number in 8 bits is 80. To extend that to 16 bits, we simply add more zeros to the left. To extend that to 32 bits, we simply add even more zeros. Recall that this is called zero extension. We discussed an instruction called ZE that 0 extended an 8-bit value to a 16-bit value. So how do we do range extension for a 2's complement number? That's easy. We'll take whatever the sign bit is and extend it to the left. For example, a negative 128 is a hex 80. If we're going to extend that from 8 bits to 16 bits, we're going to take the sign bit and we're going to extend it to the left. In the hex representation, that's going to be the same as adding F's to the number. So a negative 128 in 16 bits is an FF80. In 32 bits, it's a quad F FF80. Why does this work? Why can't we just add zeros? If we extend by zeros, what's going to happen is we would take this number and we would get a 16-bit number 0080. Now taking our negative number and now made it positive. So we have to preserve the sign, and we do that by extending it to the left. For a positive number, we do the same thing. Here's a positive 127. It's a hex 7F. To extend that to 16 bits, we'll take that 0 and extend it out, and we'll get a 007F. This is called sign extension, and it simply copies the most significant bit to the left in the extended range number in order to preserve the sign.